telling me that. Okay. Well, we'll go ahead and get started here then. So again, just time for review. So please, if you have any questions, I'm happy to take those now, and we'll kind of run through some questions, get some problems done. If we get to a point where we don't really have any, I can try to come up with things as well. So, what questions we got? Yeah.
We just start with number one.
Start with number one.
This one's killing it. It's like super easy, but I can't. Where's it?
Okay, so it's so this is number one on the study guide. And the problem is x cubed, it's x cubed minus x squared plus 2x. I was just I'm making a type of thing with the solution so you can check your answers to the problems you did. Okay, so we have this problem, we want to figure out where the critical points are, and we want to be able to graph it. Okay, so how do I figure out where critical points are in a graph like this? Good. So maybe for just know what the questions are. So find critical points and sketch. Okay. So yeah, so we find the derivative, right? Because we need to figure out those critical points are going to be the places where either the slope of my tangent line is 0 or that the function is undefined, which for all the problems in our case, I gave one that kind of has an undefined part to it, but the test ones will generally just be a polynomial. So no need to just make sure to understand these. So I'm going to take the derivative. So what's the derivative of f of x in this case?
3x squared.
Okay, and then I take this, and I set it equal to 0. Okay. So we can't factor that. Okay. So normally we would test to try to figure out how to factor this, right? We would see if there's any sort of factors, but unfortunately there's not any factors that make this work. Okay. What other ways do we know how to solve quadratics? Quadratic formula. Good. What is the quadratic formula? Just in general.
Negative b
Negative b.
plus or minus b squared. B squared minus 4ac.
Good.
All of this row.
Awesome. So this is the quadratic formula, right? If you, for some reason, you're on the test and you can't, for the life of you, figure out how to factor the quadratic you have, then you always have the quadratic formula to use, right? So in this case, we're going to take our numbers and plug in, right? So we're going to get negative b, which is going to be negative 2, right? Because 3 is a, negative 2 is b, and positive 2 is c. So I'm going to get negative 2, which is positive 2, plus or minus the square root of b squared, which is, what's b squared in this case? 4, good. Minus 4 times 2 times 3, and that's all over 2 times. Okay. Good. So watch what's going to happen, right? We're going to get 2 plus or minus the square root of, so 4 times 3 is 12. 12 times 2 is 24. 4 minus 24 is negative 20 over 6. This is a problem. We're only dealing with real numbers, okay? I'm not expecting you guys to pull out complex numbers to do these problems. So this is bad. You don't have this. Okay? So we can't use these. These values that solve that equation, we can't use them. So that means that for this equation, there is no real solution. Right? Because if there's no x and without an I part on it that makes that true, then there's no real solution to it. right? So how many critical points do I have? Absolutely none. There are no critical points on this graph. So no critical points. Okay. But I still need to figure out maybe if the graph's increasing or if it's decreasing, right? I'd still like to know what it's doing. But I can still do that, right? I don't need critical points to say that, right? If I have no critical points, all that means is that my graph is just going to be doing the same thing the entire time, right? Normally, I would kind of draw another line and then I put my critical points on there and then I test either side. But now I just won't have these spots. So it's always doing the same thing, right? So pick any number you want to. Okay, great. Zeros are really easy, right? If I put 0 inside f prime, I'm going to get 3 times 0 squared minus 2 times 0 plus 2, which is what? 2. And that's greater than 0, right? So every value gives us a positive number, which means that this graph is always increasing. Always. There's never a point where it's not increasing. Okay, is that good? Okay. Now, normally it's nice to have the critical points so we know where to plot things. So we may need to find an easy point to plot this graph, right? But again, to get one, why don't I just use 0, right? What's f of 0 going to be in this case? 0, right? Because I'm going to get 0 to the third power minus 0 squared plus 2 times 0, which is 0. Good. So I have 1 point to kind of gauge everything, which is 0, 0. And then my graph's always increasing. So it's going to look something like that. If you don't get the curving right exactly here, it's okay because I don't ask for the question. Especially on the test, I have little things where you need to put the answers. So I will specifically ask for inflection points or concavity if it says it there. Okay, if it doesn't, then you don't need to give me that. You don't need to worry about putting it on the sketch. So this is great. Okay, so that's it. I thought that was a good example you're doing the process to find the critical points, but realizing what you still do even if you don't have it. Okay, any questions or comments there?
Can't do the second derivative test. I looked at the actual graph and it does have concavity to it. So it just breaks it. It's just an outlier.
Yeah, well, it's just because it usually uses a second derivative test when you have critical points, right? But if we don't have any critical points to test, then we can't use the second derivative test. So therefore, yeah, you wouldn't really use it. So first derivative test is kind of required on this question. You can only use second derivative test if you have critical points because you plug the critical points into the second derivative. Okay. Good. Here's number 1. I tried to include a couple problems from each section, so you can probably tell that each section has at least a couple of problems associated with it. Yeah, they should.
I was going to say
Number 3, yes. Okay, good. I'm going to see if I can remember what it is. I think it's
find the minimum, maximum, and intervals of concavity with the inflection points in sketch.
So it's x to the 4th
Minus 32x plus 3.
Yes. Thank you. I hope everybody saw my alert message to change that to -32. I originally meant to have it like that, but for some reason, I didn't let it submit it like that. So let me just real quick address what it is. So I'll leave it. So it's 32x plus 3. I think I have it right. Now, if this was 16, what would happen is you'd get f prime of x is 4x cubed minus it'd be 16. But if you factor this, you get 4 times x cubed minus 4, which doesn't really have any nice solutions. So for the sake of giving you a nice one to know what the test would be like, I changed it. Okay. So this one, you're doing the whole thing. We're just doing the entire process, right? So this is number 2 or number 3. entire process, and I want to figure out what my min and max are, inflection points, et cetera, et cetera. Okay, so again, how do I start with that? How do I start doing all this?
Get the derivative.
Yeah.
First derivative
So take the first derivative, which is going to be what?
for x cubed minus 32.
Okay. Okay. Now that I have that, what do I do?
Then you can factor that to for x cubed minus 8.
Good, so that's a little bit simplified. There is technically a formula to factor this down, but it's not required for this question. So we need to do set this equal to what?
0.
0. Because that's how I find my critical values, right? So what do I do now? Yeah, so you can divide by 4, you know, or you can just take, also since these both are factors, I could just take this one and set it equal to 0, but in any case, I'm gonna get x cubed minus 8 equals 0. Okay, which is the same thing as x cubed equals 8, which is, what's x gonna be? 2. 2 cubed is 8. Okay, so 2 is our critical value, right? Which I'm going to be using on another line. How do I figure out what the critical point is? Okay, so I take my critical value and plug it into the original function. So critical point is 2 f of 2. It's going to be 2, and that's going to be 2 to the 4th power minus 32 times 2 plus 3. Okay, everybody calculate that? I think it'd be negative 45. Okay. To negative 45. Well, we have to, we're not sure yet. We found it's a critical point, but we haven't established if it's a min or a max yet.
Oh, okay.
Okay, that's where the first or second derivative test comes in. Okay, so for the sake of giving options here, right, we want to do both. Okay, so up top here, I'll do first derivative test. Right, so I put 2 on my number line, and I want to see whenever I'm increasing or decreasing on my graph. Right, so how do I do that? Good. So we pick a point on each side because one value on this side is going to represent all of the values on that side. And the value on the right side will represent all the values on the right side. Okay, so let's pick a value on the left of 2. 0, great. You can choose 1, but 0 is even easier, right? Don't feel like you just have to go 1 down. You can go as many times as you want. Okay, so we'll choose 0 here, right? So I need to see what f prime of 0 is. So if I put 0 into f prime of x, what do I get? If we get 4 times 0 cubed minus 32, which is negative 32, 2, and that's clearly less than 0, right? It's negative. So on this side, everything is going to give us a negative in the first derivative. So that means that we're doing what? So yeah, we are decreasing. Good. Now, give me a value to test on the right side. 3. Okay. So we'll do f prime of 3. Plug in. Let's see, 3 cubed is going to give me 27. 27 times 4 is 108. Yeah, minus 32.
76.
Yeah, 70. So 76. But in any case, clearly, whatever number you get with 4 times 27 is going to be bigger than 32. So you can either calculate it all the way or just say, look, it's got to be bigger than 0. I don't want to do the work to get there, but it's going to be greater than 0. So everything over here is positive then. So what does that tell us about that side of the graph? It's increasing. Good. Awesome. So now we can conclude that that's a local minimum because I'm going down before 2 and we're going up after 2, right? It's kind of a valley of the graph. I go down and then I pick back up afterwards. Okay, good. Second derivative test. Right? Would also work for this, right? To figure out if it's a local max or min, right? So on the second derivative test, I need to find what? The second derivative, right? Good. So what's f double prime of x gonna be in this case?
Well, that's squared.
Good. Okay, so we have 12x squared. Now I want to take our critical value, right, which was 2, and plug it in, which will give me 12 times 2 squared, which is going to be 48, right, which is very much clearly greater than 0, right? Good. So what is the concavity at that point? It's concave up. Good. Whenever we have a positive value, whenever our second derivative is positive, the graph is concave up. So we're up like a cup, or up kind of like a smiley face, you know, it's a happy one there, right? Happy curve. And so in that case, our point has no choice but to be a minimum, right? You can't have a maximum on a concave up curve. It has to be at that minimum point. Okay. Likewise, if this was negative and you get concave down, it would have to be a maximum. Okay. So in this way, we can also say that the point we just found here, the other test is a relative minimum. Okay. Good. So that is the first part of the question. Doing all the critical point stuff, right? So now we need to find the second part, right? Do intervals of concavity and inflection points. Okay. So how do I find all that stuff? So we're going to take the second derivative. If you use first derivative test, you're going to find it now. If you did second derivative test, just pull it back up here. And I do all of this. Equals 0. Good. So you can feel free to try to do some work on that if you want to. But what's x going to be? The only option for x is 0. Okay. Any other number is going to make that. It's going to make that not 0. Okay. Good. So x has to be 0 in this case, right? So for this, I need to make another number line, right? So let's establish this one was for f prime. That's for the first derivative, and this one was for the second derivative, f double prime, right? And 0 is kind of the critical value or the inflection value, possible inflection value, right? How do I find the point that corresponds to 0? Good. So it's going to be 0 f of 0, which is what's f of 0? Just 3, right? You have 0 to the 4th minus 0 plus 3. So it's 0. Okay. So we have the point 2, negative 45, and 0, 3 is points to kind of direct our graph. Okay. Now, how do I figure out where concavity? Again, we're going to take a number to the left and take a number to the right. Okay. So if I take a number to the left side and plug it into f double prime, give it what's the number to the left of 0? Okay. If I plug -1 into the second derivative, what do I get? You get positive 12, right? So I'll even 1 is 12 times -1 squared, which is going to be 12, which is greater than 0. So here we are concave up. Okay. What about give me a number to the right of 0? Good. So we have 12 times 1 squared. 12 0. So what are we doing over here? We're also concave up. Okay. Is 0 an inflection point? Absolutely not. Inflection points are only inflection points when they change the concavity. 0 is not an inflection point, therefore. It's just kind of like a dull point in the middle. It just kind of takes a quick break before being concave up again. So, good. Okay, so Therefore, we have no inflection points. If I were to ask you the interval on which we are concave up, what would you say the interval is? Almost, not quite. Negative infinity. Infinity. Good. So yeah, you still have to consider that 0, because technically to say that you're concave up at 0 is incorrect. So it's gonna look like it's concave up to the whole graph, but you still have to, we have to be a little nitpicky. Consider that stuff. Okay, so we're concave up on negative infinity to 0 and 0 to infinity. Okay, good. I got everything. So what's my last step? Scrap it. Great. We have a couple points. We have 0, 3, and we have 2, negative 45. So I'll say this down here. Okay. Now, so before 0, right? Well, we'll kind of take each of our points and pass section off the sections, right? To the left of 0, am I increasing or am I decreasing? Decreasing. Am I concave up or am I concave down? Concave up. Good. So I'm gonna have something that looks maybe like that. Okay. Good. Maybe I'll make that true. Okay. Okay. Now from 0 to 2, am I increasing or decreasing? We're still decreasing, right? From 0 to 2, we haven't hit 2 yet. Am I concave up or concave down? We're still a concave up. Good. So okay, so something like that. Just try to make sure you're getting that up shape as much as possible. Okay, finally, after 2, am I increasing or decreasing? Am I concave up or concave down? Ah, good. So we can. You have to make it. You could really just go straight to it if you want to. Again, I'm not going to be that nitpicky on it. The big thing is I better not. I just don't want to see any sort of like trying to make an adjustment there, because if you try to show that there's still something there and have the curve kind of go up a little bit, you're putting maxes and mins and stuff on the curve that are up there, even if it seems small. It's a big thing. So yeah, really, you could I could have even just said, oh, 0 is just the point on the curve, and I'll just have my curve kind of pass through it. So it looks maybe like a parabola or something. Although if you look at the graph on like Desmos or something at all, you'll see it's still concave up, but there's like a slightly weird movement on the left side. So it doesn't change. It's interesting. So cool. Any questions on that? Questions, comments, concerns? 2 is not included. I won't ask for the increase in interval, but yes, 2 makes the derivative 0, right? So we're not increasing or decreasing that. It's just a goal point. It's just kind of that. Okay, good, great. 3.1 and 3.2, going pretty good, hopefully. Try to make them simple to plug in, just do the same work and we'll be just fine. Good. Yeah. What is it? Right. So if you had a value that was like less than 0, that would mean that it's concave down, right? So that means that so let's say I plugged in -1 and it was concave up, and I plugged in 1 and it was negative, then it'd be concave down. That would mean that this is an inflection point now. Okay. Good. Any other questions? Okay. Let's go with another one. Cylinder one. Awesome. Okay. So just like that question is, I'm going to give you the equations to use. My main point is I want to make sure everyone understands how those optimization topics work. Oh.
I was just sitting there spinning my wheels for like half an hour.
Yeah, I'm so sorry about that. That's my bad. It's weird because I had written that problem before and it was correct, but whenever I transferred it, I somehow forgot that part on the problem. I was even working through it the other day and I was like, wait, that doesn't make sense. Okay, so this is number 6. 6 on the second. Okay. So number 6, we have it's 54. So we have a cylinder which has a volume of 54 pi centimeters cubed. And I want to, the question's phrased a little weird, but it's just saying I want to limit the amount of kind of covering the aluminum I use on the outside. And so in a sense, I kind of say with getting the problem anyway, you want to minimize surface area. Okay. So I give the equations for this. The volume of a cylinder is pi r squared h, and the volume, or the surface area is 2 pi rh, and then I forgot 2 pi r squared as well. Okay, because the 2 pi rh is the outside part, and then the 2 pi r squared is the top and bottom circle of the shape. Okay, so these are the 2 equations I'm going to use for this problem. Okay, so I want to minimize the surface area, right? So let's recall whenever we were working with problems like these, right? Our first question was like the first thing we had to do was to lay out all the equations, which I've given you both. So there you go. Step 1. We got 2 equations to work with. Right? Step 2, right, was to eliminate variables. What I mean by that is that I want to minimize the surface area, but the issue is that I have both r and h happening in this equation. I only want one variable. However, I know that the volume is pi r squared h, which means that 54 pi equals pi r squared h. Right? So if I want to eliminate, if I want to write one variable on this side in terms of the other, how can I do that?
H is so 54 over r squared.
Awesome.
Or, yeah, just 54.
Good. Yeah, so notice I put 54 pi just because the pi will cancel out, so it makes the math nice. So what you do, right, is I can take this equation that I know a relationship between r and h and solve it for h, or you can solve for r, but you have to do a square roots, and I think it's easier to solve for h in this case. But h is going to be 54 divided by r squared, right? You divide pi for both sides, divide r squared for both sides, and you get this. Okay. So with this being in mind, I can take that and plug it into my surface area equation, right? Because that'll allow the equation to be in terms of only one variable, right? Because h is 54 over r squared, so I get 2 pi r times 54 over r squared plus 2 pi r squared, which then I can rewrite. So I have 1 r on top and 2 r's on bottom. How many r's do I have left, and where is it? 1 r on the bottom, right? So we have 2 times 54, 108 pi over r, like that, and plus pi r. Okay. So great, we just did step 2. Surface areas in terms of one variable. So this is going to work great. How do I minimize that then? So right, step 3 is to minimize or maximize. In this case, we're minimizing. So how do I do that? We're going to take the derivative. Good. So I can take the derivative of the surface area with respect to the variable, which in this case is r. So how do I find the derivative of this thing with respect to r? Good. So let me, yeah. So quotient rule, right? So yes, we could absolutely use quotient rule here and do that. What Blaine was saying as well is if you want to, since the top is just a number, it might just be easier to take 108 pi over r and rewrite it as 108 pi times r to the negative first power. Right? So then how do I take, so now I just have a number times r to the negative first power, right? How do I take the derivative of that thing? Use power rule, right? What's the derivative going to be? Awesome. So it'd be negative 108 pi. Yes.
You would accept the answer if you did product rule.
Yeah, product rule, or if you did quotient rule, absolutely. I would be fine with that. Because you would still get the same answer, right? This way, it just the other reason I would say it's easier to do this rather than do quotient rule is because if you do quotient rule, since 108 pi is a number, you're just going to get 0 somewhere on the top, and so it just kind of adds an extra fluff that you don't need there. But you get the same answer, so I wasn't there. Yeah.
Can you go over how you converted that again?
How converted this?
Yes.
Right. So remember, if I have 1 over x and just anything, right? I just use x in this case, and it's to the n power, then I can rewrite this expression at any time as x to the minus n power. So I can bring that thing up to the numerator and just add a negative sign on the exponent, right? So in this case, I have a number on top, but it doesn't affect anything. I have 1 over r, right? Now that r is the same thing as r to the first power. So I can rewrite that as r to the negative first power. Okay, so that's how I did that.
You haven't done anything with the 2 pi r squared.
No, not yet.
Okay.
So here we get a negative 108 pi, and then you can write that as r to the negative second power, right? But I can rewrite this as negative 108 pi over r squared, again, because of that rule. If you have a negative power, you can bring it back down. The only reason we brought it back up in the first place is so our derivative would be easier. Okay, so down here, I'm gonna have negative 108 pi over r squared plus 2 pi, oh, sorry. What's the derivative of 2 pi r squared? 4 pi r. Okay. So we get that. Okay. What do I do with this thing? Set it equal to 0. If I want to find where a minimum or maximum is, I have to set it equal to 0. Okay. So make some room over here on the right side of the board. Okay. So I have this equation. Let me bring it back up. How do I solve this? There's a lot of ways, but I don't know, just give me some ideas. Yeah,
Add 108 pi r squared to both sides.
good. It's got a negative sign, so we can, if we add that, we can go ahead and get rid of that, so we don't have to worry about a negative. So we're gonna be left with 4 pi r equals 108 pi. Okay. Now what? Good. So I'll take both sides and multiply it by r squared. Why is that? Good. So that it gets it off of the denominator, brings it up. So what do I get on the left side?
4 pi cubed.
4 pi r cubed equals 108 pi. And now what? Okay. So r cubed equals, so the pi's cancel out, which is nice. 27. Good. So what's R? R is 3. Okay. Now that's not the answer to the question because I think I asked for the surface area specifically, or did I ask for the dimensions?
Surface area.
I asked for the surface area. Okay. Again, on the test, I'll have like if I ask for something specific, I'll kind of give it on the side so you know what to put in there. But it should say in the question as well. So in this question, we want to get the exact surface area. Okay. So I know the radius is 3. Maybe for easier computation, let's go ahead and find what the height is as well, right? So radius is 3. Oh, I guess we should probably check if this is the minimum, right? How could I check if it's the minimum? So we can do second derivative test, or we can do first derivative test. Is there a preference among the room?
Actually,
We'll do first derivative test in this case. Okay, so our value is 3. Okay, so where's our derivative? We have it down here. Okay, so let's see. I need to plug something less than 3 here. A 0 will work in this case because we have r squared at the bottom. That would be nice, but we can't divide by 0. So what's another one? 1. 1's a great option, right? Negative 108 pi over 1 squared is negative 108 pi, right? And we have no negative, so r is 1. We get negative 108 pi plus 4 pi. Is that greater than or less than 0? That's clearly less than 0, right? Negative 108 plus 4 is still negative. So on the left side, we are going down. Okay. Now, I bet you can guess. I would encourage you to test it. Although that will take a little bit more time. Just especially on the word all the pies and stuff. But the right side's going to be right. We'll get a positive. So what does that tell you about 3? It's a minimum. Great. So we got it. This is what we want. Okay. So R is 3. If I know R is 3, and that's the minimum, how do I find H?
into our H equation.
Yep. So we know H is 54 over R squared. 54 over 3 squared. So it's 54 over 9.
It's 6.
6. Good. So R is 3, H is 6. So then how do I find the surface area? Exactly. Let's use the surface area first. So we get 2 pi times R times H, right? Plus 2 pi times R, 3. Okay. So we get 2 times 3, which is 6. 6 times 6 is 36. 9 times 2 is 18. What's 36 plus 18? 4 pi. This is centimeters squared though. This one's still the centimeters cubed. Okay, so I didn't actually know that it would happen when I made it, but yeah, it's 4 pi. So as well. So its surface area is the same thing as its volume. Funny enough. Okay. Cool. Any questions on that? Comments, concerns? Okay. A bit of I think the harder part of the problem is just the computation for the most part. I don't think the concept is it's too bad, right? We're just using substitution, right? And solving and taking the derivative and solving for whatever the number is. We get our answer. Okay. Any questions or anything on that? Or move on. If you just as a fun fact on the side, I can't remember what the equation is, but it is possible there's a shape that looks something like this. That has, I think it's the volume is a finite number, right? So it's the surface area is infinite. So it's kind of funny how it works out, right? It's kind of like it's an object that you could fill, but if no matter how long you eat, you'll never finish it. Great. Okay, what's next? Give me another one. absolutely. Okay. Oh, can I make, it was number 8. Sine and cosine? Okay, good. I want to make a quick comment because I might have done the best job of making it clear. When I was grading the quizzes, I don't know throughout. Whenever you see the word differentiate, that simply just means to take the derivative. Okay, differentiate equals taking the derivative. Okay, so if you see the word differentiate, don't let it throw you off. I'm just using the word for derivative. How about actually on the study guide? I think all the derivative ones say differentiate on it, so you're no. Okay, number 8. Okay. So on number 8, I simply gave this problem because I need you to remember your identities, and so I gave the identities of every other trig function except for sine and cosine. Or I gave you the trig function, so you would have to work with them all to get to the answer, right? So number 8. Can you give me the expression? Wait, this is all times cotangent, isn't it?
It's all over.
I was saying it's over. Oh, I see. So I wrote it like this initially. Yeah, it would definitely be more beneficial, I think, if we, because you don't like having fractions. We don't like having fractions.
I think it's, yeah, so you can't over the tangent.
Is it?
Yeah, because I wrote it out.
Gotcha. Good. So it's cosecant x over cotangent. Good. So yes, a first step you could do is to take this and write it, right? Because it's always nasty having fractions in there. Yeah. This will be 1. I want you to write in terms of sine and cosine though. That's I don't need you to worry too much about having the identities. I want you to simplify as far as possible, but first I want you to write in terms of sine and cosine. You'll see the 1 still, but just as so I can rewrite this as cotangent x or cosecant x. Okay, that's just keep change 1, right? When we work with fractions, if you have one fraction over another fraction, I take the first fraction and multiply it by the reciprocal of the bottom fraction, which in this case, x. Okay, so now I want to rewrite everything here in terms of sine and cosine. So what's secant in terms of sine and cosine? 1 over cosine, which in this case is cosine squared, right? If you have secant squared, then it's just 1 over cosine squared, okay? If you have a power, it doesn't really change the fact that it's always cosine. You just put the extra number on there, okay? What's tangent in terms of sine and cosine? What is cotangent in terms of sine and cosine? Good, cosine over sine. Also useful to know that it's the same thing as 1 over tangent. So if you know tangent, then it's just going to be 1 over that, which yeah, you can see. Okay, cosecant. Yeah, there you go. 1 over sine is for real this time. So this is 1 over sine. Good. Okay. Good. Now, these both have the same denominator, so I'll pull those together. Right, 1 minus sine squared x over cosine squared x times, and then this is again another fraction in a fraction situation. So I'm gonna have, right, how can I rewrite this? Good. So you can cross multiply, and so in a sense what we're doing is I can rewrite cosine x over sine x. And then I'm multiplying this by the reciprocal of 1 over sine, which is going to be sine over 1. Good. Okay. Good. So notice that the signs here are going to cancel out. Okay. So now coming back to the whole idea of something turns into 1, right? We have 1 minus sine squared up here. Does anybody know what that is? Cosine squared. Good. So that comes from, remember, sine squared x plus cosine squared x 1. And so I can use this side of it. So
Are we getting all formulas?
I need to think about that. There's really not gonna be a question where you need to know it. Again, the reason I have this question is just kind of get it in your head. But there's not gonna be a question like this one. That's why I didn't have a star on it, but kind of get the formulas in your head. So you know what you're doing with your functions. But I might provide it just in case. Okay, so sine squared plus cosine squared is 1, right? But I can rewrite this by subtracting sine squared from both sides to get cosine squared x. Right? So that leaves me with cosine squared x over cosine squared x times cosine, which is 1. It's just cosine x because cosine squared over cosine squared is 1. Right? So cosine x is the answer. Yeah.
So, I just solved it as quickly as I could instead of going through all of that. I just checked, like, that's why I said that was 1.
Oh, absolutely.
Would you take points off if I didn't do it like that?
No. The reason I posed it originally is because that's not right. The reason I posed it the way I did originally is because I think that this one's easier to remember than the tangent secant one. But if you remember the tangent secant ones, all power to you. That's great. They're very useful, right? So I can always rewrite this as secant squared. This is also a Pythagorean identity. By the way, the tangent squared plus 1 is secant squared. So secant squared x minus tangent squared x equals 4. Yeah, so absolutely. This would have also been 1, and then when you flipped everything, it would have just been. Questions there? Comments? Cool. Okay. Yeah, let's anybody on this side of the room got a question from the study guide? Anyone that you're just, that looks difficult. I really want to know. Oh yeah, you. The last 2?
That was like the last
Oh, you're talking about Newton's method?
Yeah.
Yeah, we can go ahead and do those. So let's do, I think for now, so we can just make sure to get to some other questions, I'll probably just do one of those. That's okay. And preferably I'd like to do the one that's starred, which is I know the question is good. Wait, did I write it as, what's the question on this? This. Okay. So I have this equation, right? And I want to use, so I'm given that XO equals 2. So this is the initial approximation. And I want to find X1 using so Newton's method, right? We learned is that X1 is equal to XO minus F of XO over F prime of XO. Okay. What is F in this case? What do I use? It's the equation, right? So if it's equal to 0, you just use that thing, right? So in this case, where F is going to be x squared minus x minus 1. If it's not equal to 0, right? So if let's say instead of giving you that, I gave you this x cubed equals x squared plus x plus 1. You would first take it and set it equal to 0. So I would subtract and get x cubed minus x squared minus x minus 1 0. And then I would use that. Okay. In this case, it was already set equal to 0, so that's your function. But if it's not, set it equal to 0 first. And then get it. Okay. Good. So we have f of x, which is just the equation. What's f prime in this case? This is 24. What's f prime of x going to be? Awesome. And then square root of -1. There we go. I don't know. So -1. Good. So this is our derivative, right? So we need xo, which I gave you, just 2. We need, right, I give it to you, right? Or did I? Okay. We have f of xo, right, which we need to find, right? So we need to figure out what f of 2 is going to be, right? So f of 2 is going to be 2 cubed minus 2 squared minus 2 minus 1. So we have 8 minus 4 minus 2 minus 1. So we have 8 minus 4 is 4, 4 minus 2 is 2, 2 minus 1 is 1. Good? So f of 2 is 1, or f of xo. You want to think about it that way. F prime of 2, or f prime of xo, right? Again, we just plug in f prime, right? So I'm going to have, what's that going to be? Right, so we're going to have 3 times 2 squared minus 2 times 2 minus 1, which is going to be 3 times 4, which is 12, minus 2 times 2, which is 4, minus 1. 12 minus 4 is 8, 8 minus 1 is 7. Good. So 1 is f of xo and 7 is f prime of xo, right? So x1 is equal to xo. Or I'll put 2 here. 2 minus f of 2 over f prime of 2. 2 minus f of 2, which we just found is 1, over f prime of 2, which you also just found is 7. Okay. Now it would be preferable to write this as just one fraction. So how would I write this as one fraction? Right. How do I get the 13/7? 14 over 7, right? So we need to get a common denominator, right? I can't combine 2 different fractions together and stay the same denominator. So I'm going to multiply 7 over 7 for that number, and I get 14 over 7 minus 1 over 7. Which is actually a pretty good approximate of that number. And that would be it. I only answer right. Okay, so if you have a computation like that, it's just going to be something like that. The sign, of course, the sine ones and the cosine ones might be, a little weird. But I don't have one like that. So don't stress. You can use 25 as an example practice. 13 over 7 is all we need. Okay. You want to find, if you just have time to test and you're just really bored, you can keep going. I always find this one that's going around with this that equation. Because this equation gives us the solutions are, well, one of the solutions is whole ratio, which is a nice number. So I always like to see what the solution is. But it doesn't have a nice plus. Okay. Good. 24. Great. Need another one. $23. Is that the quotient inch one? Okay. Yeah. Okay. What specifically is the equation? X cos squared of 4x. Okay. And so I want to differentiate this, right? Which means I want to take the derivative of this, right? So to take the derivative of this, what do I need to do? What rule should we immediately think of when we see that? product rule first, because I have x times coach squared 4x. Okay. I can't take this x and put it inside the coach, okay, to make it work out that way. So I need to use product rule here, right? So product rule, right? Again, remember, if I have the derivative of u times b, there you go, equals u times dx du over dx, right? What should I call my u in this case? X. What should I call my b in this case? Okay, so let's take care of the easy one first. What's du over dx going to be? 1. Great. What's dv over dx? This one's going to take a little bit more work. Let's take it slowly, right? What should be my first step? So we're going to be using general power rule, right? Because we have a function of x that's raised to a power, right? Please keep in mind that this statement is the same thing as saying cosh of 4x squared. Okay, so that 2 there is just saying it's squared. The reason that we write it like this is because if you just leave it here, sometimes that can be confusing with the argument, and just gets people get a little confused when you write it like that. So this is just a general notation, but it means, okay. So what would general power rule say for this question? What is it? Move 2 to the front. Good. And then what? What is it? Rewrite the inside, right? Don't take the derivative yet of the inside. What's the power? It's 1 now, right? Because we do 2 minus 1, right? So we get 1. Okay, now we multiply by the derivative of the inside. Okay. What is the derivative of cosh of u, right? Because we still don't have x inside. We have 4x, right? What's the derivative of cosh? Sinh. So we take sinh, and again, I need to carry this 4x with me. And what's the derivative of? So now what do I multiply in the end? 4. Okay, good. So let's recap what happened, right? Whenever I took the derivative of this thing, I had a function of x to a power, right? So I did general power rule, and then I said, let's multiply by whatever du over dx is, right? Well, u in this case was cosh of 4x. So there had to be another chain rule, right? Which is just our, the one we learned, or by the derivative of cosh u, right? Right. So again, I write down sinh 4x and then I multiply by 4 at the end. So there's a couple of chain rules happening. So if you need to explicitly kind of write your, write d of this thing over dx and take your steps out, then that's fine, right? But keep in mind, there's a couple of levels we're moving through. Okay, so that's really the hardest part of the problem is getting that. Yeah.
If coach wasn't squared, would sinh still be there?
Yes.
Okay.
So you're saying, so if we're taking the derivative of just cosh?
Yeah.
Right. Well, if I was taking the derivative of cosh of 4x, right? This is going to be sinh 4x times du over dx, 4, right? The sinh would still be there, cosh wouldn't. The only reason cosh gets left behind is because it's to a power, right? So general power rule happens. Okay, does that make sense? Is that good? Okay. Am I done?
No.
Nope. We need to write out the actual derivative, right? Let's dy over dx. Good. So it's x times dv over dx, which is all of that. right? Which I'll do 2 times 4, which is 8. 8, and then, so then we have cosh 4x, and it's just to the first power, so it's just cosh 4x times sich 4x. Okay. And then what? Plus what? So plus v, which is cosh square root of 4x times du, which is 1. That's u, right? We had the derivative of u times v is u times dv over dx plus v times du over dx, right? So we need to make sure that that x sticks around. You might have noticed at this point, even on the study guide, I think most of the time if I were using product rule, I just put x on the front typically. So this is give you an extra step.
Can we run through the 8x at the beginning?
No, I wrote it like that just so we can see u dv over dx and v. But if you put 8 on the front, that's fine, right? All multiplication is commutative, right? Which means that if no matter what order they're in, I'm getting the same answer. Good. Other questions? Yeah. Okay. We have 15 more minutes. Okay, so if you got a really pressing one, you gotta ask it now, right?
I just got started on mine, but I haven't started on mine. I wrote it down. So we do that.
Let's wait. Number 9 is that the tangent squared cosine squared one? Okay.
Let's see if it has a order instead.
So, does anybody have a like one that's harder? They want to suggest.
Just don't this one.
No,
I haven't
no,
wrote down it.
I think 9's a great example because I designed 9 the way I did for a reason.
Are there going to be questions like 9 on the test?
There will be. The reason so actually I took this, I had made a study guide for 165, and I took this question from that one, except I added the squares on because I really want to emphasize what happens with powers. Okay, because I'm still seeing that sometimes that can get missed as we're doing these things. What happens when I bring the power down? Okay, so 9 is it
5 10 squared x minus 3.
5 tan squared x minus
3 cosine squared x.
I want to take the derivative of this thing. Okay. Okay. What rule do I need to use here? The general power rule, right? Or, a lot of this can come under the general branch chain rule. Anytime you have a U thing, it pops out. But yes, it's power because we know power. Both of the tangent and cosine function just have x in them, so we don't need to worry about doing anything. U thing with them, right? So f prime, right? Again, f prime is the same thing as the derivative of f, right? How do I carry that out? So we're going to take, right? So we're going to take 5 times 2,
10.
right? Which is 10. Okay. Times tangent x, what power? To the 1. Yep. So I'll just put 1 there so we can't do that. Okay. Not minus yet. We still have to add on something, right? General power rule is correct, but the general power rule says that I do bring the power down, subtract 1 from the power, and then I multiply by 1. By du over dx, right? So I need to multiply, right? So 5 2 tangent x to the first power times du over dx, which in this case, what's the derivative of tangent?
Secant squared x.
Secant squared x. So let me reiterate again. We have u is n minus 1, right? Times u over dx. Okay, that's general power rule. That's chain rule. That thing pops out. Okay. Minus And now, how do we do 3 cosine squared x? General power rule again. Good. So we have 3 times 2 times 6. Good. Cosine x. The full power first.
Times dx, which is negative sin x.
Negative sign. Good. Awesome. So then you can simplify and write this down again, but this is basically the derivative. But I'm going to get 5 times 2, which is 10, tangent x, squared x. Now notice we have minus and minus, so that just becomes plus 6 cosine x. Yeah. What is the derivative of secant squared? This and this you need to know. Okay. We'll definitely miss that question if you don't know these two ideas. Okay. They also have the u1 by extension, right? Where if I have, so if instead this was tan u, right, then this would be secant squared u over dx. And then if it was secant u, then it would be secant u tangent u. But we need to know these. Okay. You can technically always derive them because tangent sine over cosine. So then you could just do quotient rule in that case. And same thing with secant, but we really need to have these done. Okay. Good. Further questions on that?
Or if it was just tangent x, you wanna have to use the chain rule?
No. If
Because it's tangent squared x, you have to use the chain rule then?
you have to use, yes, because it's tangent to a power, right? So I need to factor in that power. If I was just taking the derivative, right, of tangent x, then that would just be secant squared. But because I was taking the derivative of tangent x, tangent squared x, or tangent x squared, it has to be 2 times tangent x to the first power times d over dx, which is secant squared. Okay. Yes, if it was just tangent x, you wouldn't have to worry about all that. You know, leaving the tangent there, it would just become its derivative. Good. Okay. Great. Let's see. Question. I will. I will be in I'll probably be in my office. There's a few people that still need to take the quiz. Please come down and take it, or if you're taking it tomorrow. But yeah, I'll be down there and also be in the MAC tomorrow. At least from 12 or 30. Be there for a while. Please stop by if you have any questions or if you just want to work one-on-one as well. Okay. Are there any other questions we can work? Do we want to work right now? Does anybody have one specific? I can also try to pick one, or yes. I'm not sure which. Are you talking about the logarithm expansion ones? Or you gonna the same one? Okay. Yeah. Absolutely. I have a question like that on study guide, and there'll be one like this on the test as well. So let me reiterate, there's stars, so you'll know the ones that are starred on the study guide are basically what the questions are going to be. Aside from they'll be changed a little bit. That's obviously I don't want you to just copy the same exact problem essentially. But all those are the concepts that you need to understand. And this expansion one kind of comes in a couple different flavors essentially because on the test, because one is just expanding it, right? So it's gonna be a little bit harder one to expand. The other one is you still need to expand it to take the derivative. Because it's easier to take the derivative that way than having to worry about taking it as it is, right? So what's is this number? What's the expansion one? 20? Okay, what is the logarithm? Is this the one that's the derivative?
Yeah.
Okay. There's one that's just an expansion too. Can we do that one? I'll leave this one up. Let's do that one first.
Oh, yeah, that's
19.
That's long base 2.
Eight x. So I want to expand and simplify this as far as possible. Okay. So this is okay. Okay. So let's start with this guy, right? How do I expand log base 2 of 1 over 8x to the 4th power? What's first step? Good. So that division there is the big guy in the middle. It's divided, right? So let's take care of that first. So if I take care of that, it's going to be what? Log base 2 1. Good. Good. Log base 2 8x to the 4. Yes, so please keep in mind, if I have log of a, base a of m divided by n, this is log a of m minus log a of n. Okay. Now what do I do? Good. How should I expand that? Question, is what I have written here correct? Well, so we will simplify further. I just want to know if what I just wrote here is the same thing as what I just wrote here, like if they're equal. No.
Oh, okay.
Please keep in mind that there's a minus sign here, and if you split this up, it has to go with both. It can't just go with the first one. Okay. Please watch out for that. Okay. So minus those two things added, I subtract both. Yeah, it was almost correct, but slightly off. Okay. Okay, let's see. So what else can I do now? So this step here is the one that a lot of people forgot to do on the quiz. Because there's still things with powers that I can bring down, or I can change. And so you need to bring down those powers. This technically is an expansion, but it's not the full simplified expansion because I can make it so much easier this way. Okay, so let's kind of work our way from left to right now. Log base 2 of 1. Wait, what's that going to be? That's 0. Okay. Why is that 0?
It's 2 to the first power. Sorry, 2 equal 2 to the 0 power equal.
Yeah, 2 to the 0 power equals 1, right? That's the same thing as 2 to the x is 1, so x is 0. Okay. Okay. Minus. Okay. So I want to actually have them like this, so if you forget to do this for any reason, that'll be okay. Can I rewrite 8 in some way, shape, or form? That'd be helpful in this problem. Was it? Yeah, so this is going to be 3, right? Good. I was thinking, I heard 3 and I was like, wait, because at first I was thinking 8 is the same thing as 2 to the 3rd power, right? And then bring down the power. But yes, 2 to the 3rd power is 8, so it would just be 3. Good. Can I rewrite log base 2 of x to the 4th power?
4 log is to.
Okay, what's my final answer? Right, so remember that minus has to go through both, -3 -4 log 2 of x. Okay, so this and that are equivalent, but this is the fully expanded version. It's a lot easier to work with. Okay, we don't have a lot of time left, so we can go and do this one real quick. This one's going to expand similarly. How would I expand this one? So we start with division again, right? So that's going to be natural log of 4x squared minus natural log of x cubed plus 4. Good. Can I expand it any further? Why not?
You're taking the derivative of this.
Right, yeah, but so I can't expand this one. Can I expand this one?
Yes.
Yeah, how can I rewrite that? That's 4, sorry. 4. Okay. Any other fixes I can do on this? Yeah. This is natural log of x squared, right? So I can take that 2 and bring it down to the front. So I get natural log of 4 plus 2 natural log of x minus natural log of x. Yeah, so this is the simplest form of this. Okay, so now what is the derivative of what I just wrote here? So let's go step by step, right? What's the derivative of the natural log of 4? No,
0.
0. Natural log of 4 is a constant, right? It's just a number. You're saying e to what power gives me 4? That's a number, right? Okay. Plus 2, what's the derivative of the natural log of x? 1 over x. Good. That's one we need to have in our toolkit right here around with us. That's natural log of x is 1 over x. Okay. Minus, how do I take the derivative of natural log of u? Actually, wait, let me ask real quick. Does everybody understand why I can't expand this all the way? Because it's addition, right? If this was just x cubed, you could, but it's x cubed plus 1. Anyway, how do I take the derivative of the natural log of u? Okay. 1 over u, so you do it as you would typically, 1 over u, and then multiply by du over dx. Okay? So again, chain rule, here's working, right? I take the thing on the inside and put it in the denominator, and then multiply by its derivative. So what would that look like in this case? Okay. Okay. If you want to simplify further, you can. Any questions on this that everybody would maybe would like to hear as well? Yeah. Huh? That's no, so what I did on this step is they're multiplying, right? Remember, if I have natural log of m times n, this is natural log of m plus the natural log of n. When I did that step, that was here on this guy, right? Because it was just x to the second. And then I could bring the two. Yeah, if you just had something to, yeah, if you had something multiplying with that thing, you have to kind of expand it using this one first. Okay, good. I think the only major thing we didn't cover today is inverse trig. So please know how to do your inverse trig function. There's a couple of questions about that. So you can always go to me with questions as well about that. I can give my hours, so please come visit. If you need to take a good look at it, you can either head there now or you can. Question? Yeah. Absolutely. So, yeah, I can do that. Is there anybody, I think I've given everybody else with you, so.
I just have a question.
Yeah, you have, oh, you have a pen. Great, okay, so do I just. I will match their comments. Three, today's seven. There you go. Yeah, no problem. Okay, yes, question. Yes, so, we didn't get to talk about the inverse trig functions today, so let's recall that real quick. So if I'm taking the derivative of, right, this is just in general, arc sine of u, it looks like, so did you?
No, okay, got it. Right.
You,
Finding the square.
right, oh, okay, you just need to figure out, remember how to find the derivative of square root of x?
Yeah, yeah.
Good.
I don't remember.
Yeah, so if I have square root of x, right,
Yeah,
can I rewrite that as an exponent?
yeah.
X to the, not x to the negative 1/2, x to the positive 1/2. Yep. So then,
But my case has square.
well, remember, that's what I was wanting to get at here. If I have arc sine of u, this is 1 over the square root of 1 minus u squared. And then multiply by not the derivative of u squared, the derivative of u, right? So u in this case was the square root of x. So I don't multiply by the derivative of square root of x squared, which would be 1, I multiply by the derivative of the square root of x.
That's how I got one.
Okay.
Square root times square root.
That makes sense now. I see that. So thank you for the clarification there. But yeah, so it needs to be whatever the derivative of u is in that
Also,
case.
this right here.
Exactly. So then you get, so you would have to multiply by 1/2 x to the negative 1/2, which is where, why I wrote that over 2 square root of x. The derivative, so we have 1/2 x to the negative 1/2 power. Yeah, well, this isn't even just regular power rule, right? Because it's just x. If I had like,
Oh, yeah, you can the one.
good. And so that's where that 1 over 2 square root is.
And this just means expanding, right?
Yeah, so all you need to do is to expand it as far as possible.
And this one I had to do the two.
And then just make sure that square root, you can rewrite that as to the 1/2 power, and so then that can come out as well. Yeah, so if I have natural log of the square root of x minus 3, then this is the same thing as the natural log of x minus 3 to the 1/2, right? And then the power can come down. Well, this is not for derivative, that's just for the log, right? That's what I wrote, natural log of m to the k power is k times the natural log of m. So that's what I just did. Does that make sense?
Yeah.
Yeah, I think, here, again, I think, I think your power was just wrong. It should be 1 here, you just forgot the negative 1/2 power. Your derivative was right otherwise.
The variable was right.
yeah. Yeah, yeah,
Okay,
and then you just forgot the power on it, so.
okay.
Otherwise, it was great, yeah, no problem. Are you coming to my?
Yeah, I have a quick. Couple of things. I did have a question about derivatives of numbers 2 of power where the variable is in the power. I mean, terms like.
Are you talking about like,
Yeah, 3 to the x, yeah, so are we ever gonna have a situation where we're gonna have the x in power and the things?
basically? So, I gave those in class, which you can always review over those in YouTube, but those will be.
I'm just trying to work through them, like, because it's rewrite, so 3x times element times one. X would, if it was 3x, for example, would just be on a 3x.
Well,
Or is there, I'm trying to think of how the power rule works out.
so it's, well, neither rule necessarily works in this case, which is why it's important. But if I have 3x to the x,
Oh, I remember. This
Right,
is
I
the
have
one
to
that,
take-
yeah, this is why I'm asking, my brain was just not working.
then you
Ah,
can take the derivative of that and solve it for y,
I remember.
or for the derivative in that case. Or you can do, I have another method as well, which we do, but I wouldn't, I won't have one like this, it'll just be something like this.
Okay.
Actually, it may actually be have a base of 3. So, there you go.
This room isn't used after, it's like got an open block, right?
Yeah,
Okay.
yeah, it's empty, which is nice, because I can let you in longer for the test, which is in person now. I realize that if you offer people the chance to take a test online, no one comes in person.
Yeah, I work at the university full-time and it's full-time remote, except I'm on campus for classes, and that's the only time I come.
Gotcha. Yeah, I can understand that. Okay. I should have people that need to make up a quiz, so I'm gonna head to the Mac, but. Oh, my computers are recording too. Hey, thank you for sticking around so long. For those of you who are watching, hopefully this has been helpful. You get to hear some of the questions as well. It's great, so have a wonderful